So let me see the problem, how to design an array of vectors using impulse invariant method. Okay. So we are going to find the h of s for h of s is equivalent to s plus a divided by s plus a the whole square plus b square. Okay. So this is when we are making a sampling over here. So easily we know that the value of s plus a, there is the Laplace transform of the value s plus a divided by s plus a whole square plus b square is b equivalent to cos to the power of b and t. There is e to the power of minus a and t into the value of cos of b and t for n is greater than or equivalent to 0. Okay. So when we are taking over here, h of z is equivalent to summation n is equivalent to 0 to infinity e power minus a and t z power minus n. So this will be replaced by e power j b and t plus e power minus j b and t divided by 2. Okay. So then after that we'll be replacing that. So 1 by 2 to be out over that. Then we'll be simplifying the expression by multiplying the value of e power j b and t and e power minus j b and t. So it is equivalent to e power minus a minus j b t z power minus 1. Similarly, e to the power of minus a, then j b t into z power minus 1. So when you are taking over on it, it will be equivalent to 1 by 1 minus of your numerator factor and 1 by 1 minus value. Then after that, we have to do the multiplication. So we'll be getting of an 1 into 1 minus of this value and then plus of this value. We have to take a numerator 1 into 1 minus of that value plus 1 into 1 minus e power minus a minus jb t into zt. Okay. So then after that, by simplifying, we'll be getting the expression h of z is equivalent to 1 minus e power minus at cos bt z power minus 1 divided by 1 minus 2 e power minus at cos bt z power minus 1 plus e power minus 2 at z power minus 2. So this is the way to do the problem for the given expression. So next, similarly, when we are doing over that, ha of s is equivalent to s plus 0.1 divided by s plus 0.1 whole square plus 9. By using the above example, so let me replace the value of a is equivalent to 0.1 and the value of b is equivalent to 9. Okay, actually b is equivalent to 3 because 9, 3 squared. 3 squared will be 9 over on it. Okay, so using that formula, let me replace over that a is equivalent to 0.1. So what will happen? 1 minus e power minus 0.1 cos of 3 t. What's the value of t over here? If the t is not given, we can make an assumption that t is equivalent to 1 second. So cos of 3 z power minus 1 divided by 1 minus 2 e power minus 0.1 cos of 3 z power minus 1 plus e power minus 2 into 0.1 z power minus 2. So then after that, the value of e power minus 0.1 will be 0.9048. Cos of 3 will be minus 0.9899. And then while you are simplifying 2 e power minus 1 cos 3, it will become 1 plus 7.91 z power minus 1 plus e power minus 2 into 0.1 will be 0.818. So after simplifying the numerator factor, we'll be getting that value to be 1 plus 0.8956 z power minus 1 divided by 1 plus 1.7915 z power minus 1 plus 0.818 into z power minus 2. Okay, so this is the way to do the problem. Okay, similarly, the next problem, HA of S is equivalent to 6 by S plus 0.1 whole squared plus 36. So the digital filter should have omega t is equivalent to 0.25 and using impulse invariance mapping t is equivalent to 1 second. So instead of here S plus K, we'll having of a B by S plus A the whole square plus B square. So the formula will be equivalent to, so see over here 1 minus e power minus t cos bt. Instead of that, we'll be having of an e power minus at sin bt z power minus 1. Okay, so we'll have the formula over that. So substitute the value of b is equivalent to 6 and a is equivalent to 0.1 and we'll be making an assumption t is equivalent to 0.1 1 second. Okay, So e power minus 0.1 sine 6 z power minus 1 divided by 1 minus 2 e power minus 0.1 cos 6 z power minus 1 plus e power minus z into 0.1 into z power minus 2. So when you are substituting over here, it will be equivalent to minus 0.2528 z power minus 1 divided by 1 minus 2 of this value, 0.8678687 plus 0.18. Simplifying the expression, we can able to get the value of minus 0.2528 z power minus 1 divided by 1 minus 1.7374 z power minus 1 plus 0.818 z power minus 2. So, so this is the way to design the an IAR filter using impulse invariant. So the next method is to be that we have to do by using of an bilinear transformation. Okay, let me see what are all the steps to design a digital filter using bilinear transformation technique. Okay, so for the given specification, the first step we have to find the pre-warping analog frequencies. So we'll be using the formula of omega is equivalent to 2 by t tan omega by 2. 2 by t tan omega by 2. So using the analog frequencies, we have to find the H of S of the analog filter. Then after that, we have to select the sampling rate of the digital filter. So sampling rate is nothing but then we'll be calling it as an t, and then substitute S is equivalent to 2 by t of 1 minus z power minus 1 divided by 1 plus z power minus 1. So into the transfer function, it's what we are found in the step 2. Okay, so we'll be applying the bilinear transformation of h of s is equivalent to 2 divided by s plus 1 into s plus 2 with t is equivalent to 1 second. So what we'll be doing over that? So already transfer function is given. So we'll be replacing s is equivalent to 2 by t 1 minus z power minus 1 divided by 1 plus z power minus 1. So replace now what will happen? So 2 divided by 2 into that value plus 1 into of that value plus 1, then 2 into plus 2. So simplify here, what will happen? We'll be getting often 1 plus z power minus 1 to be in the denominator. So we'll be getting often 2 minus 2 z inverse plus 1 into 1 plus z inverse we'll be getting. Similarly, this 2 minus 2 z inverse plus 2 minus 2 plus 2 z inverse we'll be getting. Okay, so this 2 plus 1 will be 3 over that minus z power minus 1. So the factor will be getting of 4. When this 1 plus z power minus 1, it will goes into numerator. This will be a whole square. So when you are multiplying over here, so this is 2 and 4 will be getting cancelled. So 2 2s are 4. So 2 3s are 6 minus 2 is s power z power minus 1. Upper 1 plus z power minus 1 whole square. So you take an 2 to actually we'll be taking over that. So we'll be taking off and 6 over that. So 6 we are taking common here. 1 minus. So 2 by 6 will be 1 by 3. It's nothing but 0.133. So again 1 by 6 factor will be in the numerator 0.166 into 1 plus z power minus 1 to the whole square divided by 1 minus 0.33 z power minus 1. So in the case of bilinear transformation, we have to replace s is equivalent to 2 by t of 1 minus z power minus 1 divided by 1 plus z power minus 1. Okay, that is the step we have to follow. So let me do the next different type of problem. Using a bilinear transformation, we are going to design a high pass filter, monotonic in pass band with cutoff frequency of 1000 Hz and down 10 decibel at 350 Hz. The sampling frequency is 5000 Hz. Okay. So here, when you are seeing up here, your pass band, which is to be given as an 3 decibel, and stop band attenuation to be 10 decibel, and pass band frequency 2 pi f, so which is to be given as an 2005 radian per second. Stop band frequency 2 pi f, so we'll be giving us an 700 pi radian per second. Here sampling frequency is given as 5000 Hz. So we know that there is a relationship between T and F. So T is equivalent to 1 by F, so which is equivalent to 1 by 5000. So we'll be getting often 2 into 10 to the power of minus 4 seconds. What is the first step? We have to find out the pre-warping the digital frequencies. It is omega p, capital omega p and capital omega s. And we know the relation that 2 by t tan omega p by 2, 2 by t tan omega s by 2. So substitute the value of t, substitute the value of omega p, and find out the value. So we have to use over here. So we'll be getting 7265 radian per second for pre-warping passband frequency, and pre-warping stopband frequency we'll be getting 2235 radian per second over there. Okay. The next we have to find the order of the filter. So order of the filter formula is to be n should be greater than or equivalent to log 10 to the power of 0.1 alpha p minus 1 divided by 10 to the power of 0.1 alpha s minus 1 divided by log to the power of omega s divided by omega p. Okay. So then we'll be using of here alpha p, alpha s, omega p. So we'll be getting the expression n is equivalent to 0.932. We have to round off the value. So after rounding off it, what will be getting over on it? We'll be rounding off and finding the value of n is equivalent to 1. Okay. For n is equivalent to 1, we know that the first order Butterworth filter is given as h of s is equivalent to 1 by s plus 1. So since we are in need to design the high pass filter, we have to use the formation S should be replaced as an omega c by S. So what is omega c? Omega c to be the cutoff frequency 7265 divided by, there is a pass band, so 7265 divided by S. So in your transfer function, h of S is equivalent to 1 by S plus 1. So this will be replaced by 7265. So 7265 by divided by s plus 1. So take the cross multiplication. It will goes into an numerator. Now then again by using our bilinear transformation, we know that s has to be replaced by 2 by t of 1 minus z power minus 1 divided by 1 plus z power minus 1. So we will be having of an so replace over on it 1 minus z power minus 1 divided by 1 plus z power minus 1. Okay. Substitute over on it, and then finally we'll be getting the expression 0.5792 into of 1 minus z power minus 1 divided by 1 minus 0.1584 z power minus 1. Okay. So this is the way to design a bilinear transformation for the high pass filter. So we have to replace, S has to be replaced by omega c by S. Okay. Thank you all. We see you next.